A silent message from the ancient cosmos is guiding our future in space. This is the light from stars that died long before Earth formed, a cosmic guidebook written in photons. By watching this video, you will understand how this ancient starlight is not just a distant memory, but a practical tool revolutionizing our exploration of the universe. We will uncover how whispers from the dawn of time map the formation of galaxies and chart a course for interstellar travel. How can a beam of light tell us what the universe was like before planets even existed? What does this silent conversation with the past reveal about our own place in the cosmos? That light, a silent messenger from the depths of time, is more than just a pretty glow in the night sky. It is a form of energy called electromagnetic radiation, a ripple in the very fabric of space itself. Every star and every galaxy is a lighthouse, constantly broadcasting its own unique story across the cosmos. The most incredible journeys are undertaken by the photons from the most distant objects. Consider a single particle of light, a photon, leaving a brilliant quasar. Its journey begins when our own planet was still a seething ocean of molten rock, a world without continents, without life. For billions of years, this photon travels undisturbed through the absolute emptiness of interstellar space. It does not age, it does not change, it carries, locked within its very being, a perfect and unaltered snapshot of the universe as it was at the moment of its departure. This makes ancient starlight the most pristine time capsule we could ever hope to find. We are not just looking at a distant point of light, we are receiving a direct transmission from the cosmic past. Learning to interpret the subtle signatures hidden within this light, the specific colors and energies it holds, is like learning to read the lost history of the universe. Every beam of starlight is a page in a cosmic autobiography, and we are only just beginning to understand the language it is written in. This fundamental truth transforms our entire understanding of observation. That staggering speed of light, 300,000 kilometers every single second, is not just a number, it is the key that unlocks the past, because this speed, while incredibly fast, is still finite. It takes time for light to travel the vast gulfs between the stars and galaxies. This simple, profound fact means that when you gaze at the starry sky, you are never seeing the present. You are looking into a gallery of the past, with each object showing you a moment from a different era. A telescope pointed at a galaxy 1 million light-years away does not show you that galaxy as it exists now. It reveals what it looked like 1 million years ago, a time when early humans were just beginning to walk the Earth. This is not a metaphor, it is a direct physical consequence. Our most powerful observatories are, in every practical sense, time machines. By building telescopes capable of seeing fainter and more distant objects, we are not just expanding our view of space, we are dialing back the cosmic clock. We can observe infant galaxies still in the process of formation, see the violent deaths of the first stars, and witness the universe in its raw, early state. This chronological map, written in light, is our only way to test our grand theories of cosmic evolution. How did a hot, dense primordial soup evolve into the complex web of galaxies we see today? The evidence is not buried in a rock, it is streaming toward us every second, a silent river of data from the dawn of time. That pristine time capsule of light requires a key to unlock its secrets. The true power of starlight is not in its raw glow, but in the hidden information it carries. When we pass this ancient light through a scientific instrument called a spectrograph, it unfurls into a full rainbow of colors. This is not just any rainbow. Within it, we find a precise pattern of dark and bright lines, a barcode etched into the very fabric of the light itself. These lines are the unique fingerprints of the universe's chemical elements. Each element, like hydrogen, helium, or iron, leaves its own unmistakable mark on the light that passes through it or is emitted by it. By reading this cosmic barcode, scientists can determine not only what a star is made of, but also its scorching temperature, its immense density, and the strength of its powerful magnetic fields. This process, known as spectroscopy, is the fundamental translator for the silent language of the cosmos. It turns a beautiful but mysterious point of light into a detailed data sheet, a quantitative report on the state of a distant object billions of years ago. Every dark line is an element that absorbed specific light on its journey, and every bright line is an element shouting its presence into the void. We are not just seeing a galaxy, we are reading its chemical identity card. We are not just observing a star's death, we are analyzing the elemental ashes it scattered across space. This is how a single beam of ancient light reveals the entire life story of the object that created it, giving us the hard evidence we need to map the evolution of the universe itself. That cosmic fingerprint, the unique barcode of Starlight, holds one more profound secret. It tells us not just what a star is, but where it is going. The light we receive reveals the motion of the cosmos itself through a phenomenon you experience every day. Think of the sound of a passing ambulance. As it moves toward you, its siren's pitch is high and sharp. The instant it passes and moves away, the pitch drops to a lower tone. This is the Doppler effect, and it works in exactly the same way with light. When a star or an entire galaxy is hurtling away from us, the very waves of its light are stretched out during their long journey to our telescopes. This stretching shifts the light toward the red end of the spectrum, an effect astronomers call redshift. Conversely, if an object were moving toward us, its light waves would be compressed, squashed together, creating a shift toward the blue end known as blue shift. By measuring precisely how much that unique fingerprint of elemental lines has been shifted toward red or blue, scientists can calculate the exact velocity of that object relative to Earth. This single measurement, read from ancient Starlight, unlocked the greatest discovery in modern cosmology. When astronomers in the early 20th century pointed their instruments at distant galaxies, they found something shocking. Nearly every single galaxy showed a redshift. The universe was not static, it was expanding, with galaxies all racing away from each other. This observation was the first direct evidence for the Big Bang theory, the idea that our entire universe began from an immensely hot, dense state and has been expanding ever since. The light from a dying star does not just tell us about its own death, it carries the echo of the universe's birth. That single discovery of the expanding universe was just the beginning. We needed a deeper look, a way to take a true census of this cosmic expansion. In 1995, astronomers performed a radical act of patience. They pointed the Hubble Space Telescope at a patch of sky that seemed utterly empty, a void darker than black velvet behind the stars. For 10 entire days, its mirror remained fixed on this single, insignificant point, gathering the faintest whispers of ancient light that had traveled for billions of years. The result was not a confirmation of emptiness, but a silent revolution in perspective. The Hubble Deep Field image revealed a breathtaking sight. That tiny, dark sliver of the cosmos was in fact crammed with thousands of galaxies, each a swirling island of billions of stars. Every single speck of light, every faint smudge was an entire galaxy seen as it was in its youth. This was not just a pretty picture, it was a core sample of the universe, a deep drill into time itself. By patiently collecting these ancient photons, We had conducted a statistical census of cosmic structure. The image showed galaxies in every stage of evolution, from chaotic, misshapen infants to the majestic spirals and ellipticals we see in our modern neighborhood. This single observation proved the universe was not just vast, but overwhelmingly populous, fundamentally changing our understanding of our own place within it. We went from seeing a sky dotted with nearby stars to comprehending an ocean of galaxies stretching back to the dawn of time. All of it was revealed by the silent, cumulative power of light we had simply never taken the time to see. This ancient light from the first galaxies is profound, but there is an even older whisper in the cosmic static. The ultimate time capsule is not the light from the first stars, but the very first light that ever traveled freely through the universe. We call this the cosmic microwave background radiation. It is the faded afterglow of the Big Bang itself, a relic from a time when the cosmos was a mere 380,000 years old. Before this moment, the universe was so hot and dense that it was an opaque fog of plasma where light was constantly trapped, bouncing between particles. When the universe finally cooled enough for atoms to form, the fog lifted and that primordial light was set free. Today, that brilliant flash of creation has been stretched and cooled by the expanding universe into a faint, uniform glow that fills all of space, a microwave whisper that permeates the entire sky. It was discovered entirely by accident in the 1960s, a persistent hiss in a radio antenna that astronomers could not eliminate. This was not random noise, it was the faint but unmistakable echo of the universe's violent birth. Recognizing its significance, scientists launched a series of space missions to listen more carefully. The COBE satellite first confirmed that this background glow had a perfect thermal signature, a blackbody spectrum that precisely matched the predictions of the Big Bang. Then came WMAP and later the Planck mission, which did something even more extraordinary. They created exquisitely detailed, full-sky maps of this ancient light, measuring its temperature with incredible precision. These maps revealed that the cosmic background is not perfectly smooth. It is imprinted with tiny variations, minute hotspots and cold spots that differ in temperature by less than 100,000th of a degree. These tiny ripples are the cosmic blueprints for everything that followed. They represent the initial seeds of density, the slight gravitational overdensities in the early universe where matter was just a little more crowded. Over billions of years, gravity amplified these tiny imperfections. The slightly denser patches pulled in more and more matter, growing steadily from small clumps into vast clusters of galaxies, and the slightly emptier patches expanded into the great cosmic voids we observe today. The entire grand structure of the modern cosmos, the great cosmic web of galaxies, was written into the fabric of the universe in its first moments. By reading this ancient microwave light, we are not just looking at a baby picture of the cosmos. We are holding the original architectural plans, the direct genetic code that determined how our universe would grow up. This ancient blueprint, the cosmic microwave background, gave us the universe's initial conditions, but the story did not end there. The expansion it revealed held a deeper mystery, one that required a different kind of time capsule to solve. We needed a measuring tape that could stretch across billions of years, and we found it in the most violent stellar deaths imaginable. Certain stars end their lives in a cataclysmic explosion known as a Type Ia supernova. These are not random events. They occur with a precise and predictable trigger when a white dwarf star steals just enough matter from a companion to cross a critical threshold. The resulting detonation is so uniform that every single one of these supernovae reaches the same peak intrinsic brightness. This consistency makes them perfect cosmic beacons, known to astronomers as standard candles. Think of a 100-watt light bulb. If you see one shining brightly, you know it is close. If you see another that appears faint and dim, you know it must be far away. By measuring exactly how dim a distant type Ia supernova appears in our telescopes, we can calculate its distance from Earth with incredible precision. In the late 1990s, two independent teams of astronomers began using these stellar explosions as mileposts. They pointed the world's most powerful telescopes at the deepest reaches of space, collecting the ancient light from supernovae that had detonated billions of years ago. They fully expected to confirm that the universe's expansion, set in motion by the Big Bang, was gradually slowing down over time, pulled back by the collective gravity of all the matter in the cosmos. What they found was the opposite. The most distant supernova, the ones whose light was oldest, were significantly dimmer than their models predicted. This was not an error. It meant these cosmic beacons were much farther away than anyone had thought possible. The only explanation was that the expansion of the universe was not slowing down at all. It was speeding up. This was a discovery so shocking and counterintuitive that the researchers themselves struggled to believe it. They were seeing the ghostly light of ancient stellar explosions, and it was telling them that a mysterious, repulsive force was stretching the very fabric of space itself, pushing galaxies apart at an ever-increasing rate. This inexplicable force, which now dominates the cosmic budget, was given a simple but profound name: dark energy. The silent light from dead stars had not only mapped our past, it had rewritten the entire future of our universe. Dark energy rewrote our cosmic future, but we still faced a profound question. What is the rest of the universe actually made of? We now know that the atoms making up our bodies, our planet, and every star we see account for less than 5% of the cosmos. The majority is an invisible, mysterious substance we call dark matter. It does not emit, absorb, or reflect any light, making it completely transparent to every telescope ever built. So how can we possibly hope to study something we cannot see? The answer lies in how this unseen mass interacts with the one thing we can observe: ancient starlight. Einstein's theory of general relativity gave us the key. He proposed that massive objects do not simply sit in space, they warp the very fabric of space-time around them. Think of space as a taut, stretched rubber sheet. Placing a heavy bowling ball in the center creates a deep dimple. Now roll a tiny marble past the bowling ball. The marble will not travel in a straight line, it will curve along the dip in the sheet. Light behaves in exactly the same way. When a beam of ancient starlight from a distant galaxy travels through the universe, it does not always travel in a straight line. If its path takes it near a massive object like a galaxy cluster, the warped spacetime around that cluster will bend the light's trajectory, just like a lens of glass bends light. This phenomenon is called gravitational lensing. We are not using telescopes to look at dark matter. We are using dark matter itself as a telescope. The light from galaxies billions of light years behind a cluster is distorted as it passes through the cluster's immense gravitational field. Sometimes the effect is subtle, causing the background galaxies to appear slightly stretched and smeared into faint arcs, like looking at a street lamp through the bottom of a wine glass. This is weak lensing. In more extreme cases, the lensing can be so powerful that it creates multiple images of the same distant galaxy, or stretches it into a perfect bright circle of light known as an Einstein ring. By meticulously analyzing these distortions, by mapping how the ancient light has been bent and twisted on its journey to us, astronomers can perform a kind of cosmic reconstruction. They can work backwards to calculate the precise amount and distribution of mass in the foreground cluster that must be there to cause such a distortion. The result is a detailed, three-dimensional map of where the invisible mass lies, and the maps reveal something astonishing. The visible galaxies in a cluster are just tiny, bright islands floating in a vast, unseen ocean of dark matter. The gravitational lensing effect powered by ancient starlight provides our most direct and compelling evidence for dark matter's existence and allows us to trace its hidden architecture. We are reading the invisible by watching how it bends the light from the long dead. These silent, ancient stars are the living fossils of our cosmic neighborhood. They are the stellar archaeologist's treasure scattered throughout the vast halo of the Milky Way. To find them, astronomers search for stars with a very specific chemical fingerprint, one that tells a story of a simpler, more primitive universe. The oldest stars we can locate have a composition that is almost purely hydrogen and helium. They contain only trace amounts of elements heavier than these, what astronomers call metals. This is the pristine signature of the first generations of stars, born from gas that had only been cooked in the Big Bang itself. There had been no previous stellar furnaces to pollute this primordial gas with the ashes of heavier elements. When we find a star with this metal-poor signature, we are effectively looking at a time capsule from an era before the galaxy's disk had even fully formed. These ancient suns are the galactic pioneers, the first inhabitants of our Milky Way. Their orbits are chaotic, often moving against the flow of the galaxy's majestic spiral rotation, a relic of the violent mergers and chaotic assembly that built our home. By contrast, a younger star, like our own Sun, contains a rich mixture of elements like carbon, oxygen, and iron. This chemical enrichment is the direct result of generations of stellar lives and deaths. Every element heavier than helium was forged in the nuclear hearts of stars or in the violent blasts of their supernova deaths. These stellar forges then scattered their newly created elements across space, seeding the cosmic gas clouds that would one day collapse to form new stars and planets. Our own Sun, with its abundance of iron and silicon, is a child of this process. It was born from gas that had been recycled and enriched over billions of years, the legacy of countless stars that lived and died long before our solar system even existed. The very iron in your blood and the calcium in your bones were created inside a star that exploded in our galaxy's distant past. By reading the chemical barcodes of countless stars, astronomers can piece together a timeline of our galaxy's growth. They can identify distinct stellar populations, each with its own chemical age and orbital characteristics, and use this data to reconstruct the Milky Way's life story. We now believe our galaxy grew from the inside out, with the central bulge forming first, followed by the gradual assembly of the sprawling disk and the diffuse halo of ancient stars. This is stellar archaeology, a discipline that uses the faint light of ancient suns to excavate our own cosmic origins, one spectral line at a time. This same principle of reading starlight now directs our search for other Earths. The ancient glow from a distant star does more than illuminate a planet. It can dissect its very air. When an alien world transits across the face of its sun from our vantage point, a remarkable event occurs. The star's light does not simply vanish behind the planet. Instead, a minuscule fraction of that light, perhaps 1 part in 10,000, skims through the planet's thin atmospheric shell. Imagine a brilliant lighthouse beacon shining through a fog. The fog does not block all the light, it alters it, imprinting its own unique signature upon the beam. In that fleeting moment of transit, the exoplanet's atmosphere acts as that cosmic fog. As the starlight filters through layers of gas, specific molecules within that alien air absorb very specific colors of light. A spectrograph captures this filtered starlight, and when it is unfurled, the rainbow reveals a new story. The dark lines in the spectrum are no longer just the star's fingerprint. They are now a complex overlay, a chemical barcode for the planet's atmosphere itself. A telltale dip at the precise wavelength for water vapor suggests a world with oceans or ice. A signature of methane, a gas often produced by biological processes on Earth, could hint at something more. The potential detection of oxygen, a highly reactive gas that quickly binds with rocks unless it is constantly replenished, would be one of the most compelling signs of all. This is how we transform a point of light into a planetary probe. We are not yet taking pictures of these distant worlds. We are reading their atmospheric recipes using the only tool we have, the ancient, silent light of their suns. This technique is already guiding a monumental decision: where to point the next generation of colossal space telescopes. Which of these thousands of dimmed stars holds a world with an atmosphere that whispers the possibility of life? The answer is written in the light that managed to travel through it. That silent river of data from the cosmic dawn now has its most powerful listener. The James Webb Space Telescope represents a fundamental shift in our quest to capture ancient light. Unlike Hubble, which sees primarily invisible light, Webb was specifically designed with golden mirrors to be an infrared observatory. This is not a minor upgrade, it is a necessary evolution for cosmic time travel. The most distant galaxies in the universe are racing away from us so fast that their ultraviolet and visible light is stretched during its long journey across the expanding cosmos. By the time this light reaches us billions of years later, it has been transformed, redshifted into the infrared part of the spectrum. To our eyes, this light is invisible, but to Webb's instruments, it is a brilliant beacon. The telescope is essentially tuning its ears to the precise pitch of the universe's earliest whispers. It is not just looking further out into space, it is looking back to a specific chapter in cosmic history known as the Epoch of Reionization, a time when the first stars and galaxies were switching on, burning away the primordial fog of hydrogen that filled the universe. Before Webb, this era was a theoretical frontier, a blank spot on our map of cosmic evolution. We had models and predictions, but no direct observations. Now we are receiving the first photographic evidence from that formative age. The images are not just showing us infant galaxies, they are revealing them in shocking abundance and unexpected maturity. Some of these very first galaxies appear larger and more structured than our theories predicted, forcing a rapid and thrilling reassessment of how quickly the universe assembled its first large-scale structures. Every new deep-field image from Webb is like turning the page on a history book we have only just begun to read, each page filled with discoveries that challenge and refine our understanding of that first cosmic dawn. This is more than observation, it is a conversation with the very first starlight, and it is telling a story we are only starting to understand. While we peer into the deepest past, another mission is taking a monumental snapshot of our present galactic home. The Gaia Space Observatory is not a time machine looking backward, but the most ambitious cartographer ever built. Its singular goal is to measure, with breathtaking precision, the positions, distances, and motions of over 1 billion stars within the Milky Way. This is not a static picture. Gaia watches the sky, repeatedly observing each of its billion targets, patiently tracking their subtle movements through space. From this torrent of data, derived entirely from the light these stars emit, a new vision of our galaxy is emerging. We are building the first three-dimensional, dynamic movie of the Milky Way. We are no longer looking at a flat, static painting of the night sky, but a swirling, living structure. We can now see which stars are moving toward us, which are speeding away, and how entire families of stars orbit the galactic center together. This precise measurement of motion, known as proper motion, transforms anonymous points of light into individuals with a known trajectory and velocity. It is the difference between a single photograph of a crowded town square and a live video feed from a drone hovering above it. Suddenly, you can see the flow of traffic, you can identify groups walking together, and you can predict where everyone will be in an hour. Gaia gives us that live, galactic scale view. The sheer scale of this stellar census is revealing the ghostly architecture of our galaxy in unprecedented detail. By plotting the precise paths of so many stars, we can literally see the gravitational influence of the invisible. When a stream of stars is seen moving in a strange, unexpected pattern, it is a telltale sign of a past galactic collision, a ripple in the stellar population caused by a smaller galaxy being consumed by our own. Even more profound, the very way stars move within the galaxy's vast disk and halo does not match the gravitational pull from the visible matter alone. Their speeds and orbits are dictated by the immense, unseen halo of dark matter that cradles the entire Milky Way. Gaia's map, written in Starlight, is therefore also a precise map of dark matter's gravitational signature. We are using the light of 1 billion suns to trace the contours of the invisible scaffold that holds our galaxy together, watching the silent dance of the seen and the unseen in a cosmic ballet that has been ongoing for billions of years. These ancient stellar remnants hold a rhythm more precise than any clock on Earth. A pulsar is the collapsed core of a massive star that exploded in a supernova, compressed into a spinning city of pure neutrons. As it rotates, it fires twin beams of radiation from its magnetic poles. If one of those beams sweeps across our line of sight, we observe a flash of light, a pulse, with a regularity that rivals atomic timekeeping. This makes a pulsar a perfect cosmic lighthouse, its steady blink a beacon across unimaginable distances. But the true power of this rhythm lies not just in its consistency, but in the tiny deviations we can detect. When a gravitational wave passes through the fabric of space-time, it creates a minuscule ripple, briefly stretching and squeezing the space between us and the pulsar. This infinitesimal distortion changes the distance the light has to travel, causing the pulse to arrive at our telescopes just a fraction of a second early or late. On its own, this shift is far too small to notice. The breakthrough came from observing not one, but an entire array of these celestial clocks. By monitoring dozens of the most stable millisecond pulsars across our galaxy, scientists create a galaxy-scale gravitational wave detector. They are not building an instrument, they are using the galaxy itself as one. The predictable light from these ancient, spinning corpses becomes our probe, feeling the subtle tremors in the cosmos that no single telescope can see. This method has allowed us to sense the slow, cosmic drumbeat of merging supermassive black holes, events so colossal they shake the foundations of space-time itself. These are not brief chirps, but a continuous hum of low-frequency waves, a background chorus from the most powerful events in the universe, all heard by listening to the impeccable rhythm of long-dead stars. The silent journey of a photon is rarely a straight shot through empty space. It must navigate a cosmic sea, a vast and complex ecosystem of matter that fills the seemingly void between the stars. This is the interstellar medium, a diffuse mixture of gas and dust that is the galactic raw material from which everything new is born. When the ancient light from a distant star passes through one of these cosmic clouds, it does not emerge unchanged. The cloud leaves its mark upon the light, a subtle interaction that tells a profound story. Specific atoms and molecules within the cloud absorb very specific colors from the starlight, imprinting a new set of dark lines onto its spectrum. This is the cosmic equivalent of a chemical assay, revealing the exact elemental composition of that distant gas cloud millions of light years away. But there is another, more visual effect. The tiny dust grains in these clouds are exceptionally efficient at scattering blue light, much like our own atmosphere makes the sky appear blue. As starlight travels for eons through these dusty regions, the blue wavelengths are gradually stripped away, leaving the light noticeably redder by the time it reaches our telescopes. This interstellar reddening is a direct clue to the density of the material the light has traveled through. By reading these subtle signatures of absorption and reddening, we can map the invisible architecture of our galaxy. We can locate vast, cold reservoirs of molecular hydrogen, the primary fuel for star birth. We can trace the swirling tendrils of diffuse gas and the dense, dark nebulae that blot out the light from stars behind them. This is not just about cataloging cosmic ingredients. This interstellar medium is the galactic circulatory system. It contains the ashes of dead stars, the heavy elements forged in supernova, which were then scattered back into space. This enriched material eventually collapses under its own gravity, forming new stars, new planets, and perhaps new life. The light from a 10-billion-year-old star, by passing through a cloud that itself will one day form a new solar system, connects the death of one cosmic generation directly to the birth of the next. We are reading the lifeblood of the galaxy itself, using ancient starlight to trace how galaxies recycle their very substance across cosmic time. Every so often, the universe sends a signal so brief and brilliant it defies all expectation. In a single millisecond, a fast radio burst can release more energy than our sun emits in 80 years. These are not the steady pulses of a spinning pulsar or the predictable light of a supernova. They are cosmic lightning strikes, flashes of radio waves from galaxies billions of light years away, and their origins remain one of astronomy's greatest puzzles. Some might be the death cries of magnetars, neutron stars with unimaginably powerful magnetic fields. Others could be the product of cataclysmic collisions. What makes these enigmatic bursts so valuable, however, is not just their power but their journey. The ancient radio light from an FRB does not travel through a perfect vacuum. On its billion-year voyage, it slices through the diffuse, ionized gas that floats in the vast spaces between galaxies. This material is so thin it is otherwise nearly impossible to detect, yet it forms the cosmic web that connects the entire universe. As the burst travels, this sea of charged particles affects its radio waves. The higher frequencies, the cosmic equivalent of a high-pitched sound, race ahead just slightly, while the lower frequencies lag behind. The entire burst arrives stretched out with its different colors dispersed. By measuring this dispersion, by calculating precisely how much the burst has been smeared, astronomers can perform a remarkable piece of cosmic accounting. They can count the total number of free electrons the signal encountered along its path. Each electron is a tiny marker, and their collective sum reveals the total density of the invisible material the light has traveled through. A single, mysterious flash from the distant void becomes a probe, letting us take the measure of the universe's hidden scaffolding. We are using these inexplicable cosmic shouts to trace the outlines of nothingness itself, mapping the ghostly threads of the cosmic web that would otherwise remain forever dark to our eyes. That same impeccable rhythm guiding our discovery of gravitational waves could one day become a roadmap for our own journeys. The guidance from ancient starlight may soon extend from mapping the cosmos to guiding human travel within it. Imagine a future spacecraft venturing far beyond the orbit of Pluto, where signals from Earth take hours to arrive. A traditional GPS would be useless out here. But this ship is not lost. Its onboard computer is listening to the steady, metronomic ticking of millisecond pulsars. These cosmic lighthouses, with their predictable X-ray flashes, offer a constant and universal timing signal. The concept is called X-nav, or X-ray navigation. By locking onto the pulses from at least 3 different known pulsars, the spacecraft can perform a simple yet profound calculation. It measures the precise arrival time of each pulse, because the exact location and rhythm of these pulsars are charted in a cosmic catalog. Any tiny delay or advance in the pulse's arrival reveals the ship's position relative to that pulsar. It is a form of triangulation, but on an interstellar scale. The spacecraft is essentially asking, where am I in this vast ocean, by comparing my watch to these unerring cosmic clocks? This technology, guided by the steady beat of ancient stellar corpses, promises something revolutionary: autonomous and precise navigation for deep space missions, completely independent of Earth. A ship navigating by dead stars would never need to phone home for directions, making humanity's future among the stars a little less daunting and a little more within our grasp. This silent messenger from the stars has done more than map our universe. It has rigorously tested the very laws that govern it. The faint light from distant suns has become the ultimate laboratory for Einstein's theory of general relativity. The theory made a profound prediction that gravity is not a force in the traditional sense, but a warp in the fabric of spacetime itself. Massive objects like our sun should cause this fabric to curve, and the path of starlight traveling through this curved space should bend as a result. The proof came during a total solar eclipse in 1919. Astronomers measured the precise positions of stars whose light was skimming past the darkened sun. They found that the stars appeared to be slightly out of place, their light subtly deflected by the sun's gravitational field, exactly as Einstein had predicted. This was not a minor observation. It was a fundamental validation that the geometry of the cosmos is malleable. Another key test involved the light from our own sun. Einstein's theory stated that light climbing out of a gravitational well, like the sun's intense field, should lose energy. This energy loss would not slow the light down, but would instead cause its color to shift very slightly toward the red end of the spectrum. Detecting this gravitational redshift required incredibly precise measurements, but once again, Starlight delivered the evidence, confirming that a photon's journey is shaped by the gravity it encounters. Perhaps the most stringent test of all came from the cosmos itself, using the impeccable rhythm of binary pulsars. These are pairs of neutron stars orbiting each other at tremendous speeds, emitting perfectly timed radio pulses. General relativity predicted that such a system would lose energy in the form of gravitational waves, causing the stars to spiral ever so slowly inward. By tracking the arrival times of the pulsar's flashes for years, astronomers watched this cosmic dance slowly decay, with the orbital change matching Einstein's equations with breathtaking accuracy to within a fraction of a percent. Every single photon that has journeyed across the cosmos, whether from a nearby star or a billion-year-old quasar, is more than a message. It is a tiny, precise probe of reality's deepest rules. This ancient light does not just show us what is out there, it actively guides and constrains our understanding of gravity, space-time, and the fundamental architecture of the universe. This silent river of data, carrying the precise values of nature's fundamental laws, forces a question far beyond pure physics. Why do these constants possess the exact values they do? The force of gravity, the strength of the nuclear forces, the mass of an electron, every single one is a dial on the cosmic control panel. We have measured these values with incredible accuracy, often by analyzing the specific colors of light emitted or absorbed by atoms across the universe. The stunning revelation is that if any one of these dials were turned even a fraction in either direction, the universe as we know it would not exist. A slightly stronger gravitational constant, and the universe would have collapsed back on itself immediately after the Big Bang. A slightly weaker force binding atomic nuclei and hydrogen would never have fused into the heavier elements essential for planets and life. The cosmos appears to be balanced on a razor's edge, a precarious set of conditions that allows for galaxies, stars, planets, and ultimately, observers. This is the puzzle of fine-tuning. It is as if the universe received a very specific set of instructions, a recipe that had to be followed with exacting precision to produce a habitable world. This observation leads us directly to a profound and often debated idea known as the anthropic principle. In its simplest form, it states that the universe must have the properties we observe because if it did not, we would not be here to observe it. We are not passive witnesses to a random cosmos. Our very existence as conscious beings is a piece of data that constrains the kind of universe we can possibly find ourselves in. This is not a proof of design or a single answer, but a logical statement that changes the context of the question, why is the cosmos so hospitable to life? One potential answer is that it could not have been any other way for us to be here asking the question. Some scientists propose a staggering vision of a multiverse, where our universe is just one bubble in a vast, perhaps infinite, cosmic foam. In this picture, each bubble universe has its own random set of physical constants. Most of these universes would be stillborn or barren, incapable of producing complexity. But in a rare few, by sheer statistical chance, the numbers line up perfectly. We, of course, find ourselves in one of those exceptionally rare, life-friendly bubbles, simply because we could not exist anywhere else. The light from ancient stars does more than chart our past. It holds up a mirror to our own existence. It forces us to confront the remarkable fact that the same laws that allow a photon to travel for billions of years also allow for the emergence of beings capable of understanding its journey. This silent conversation with the cosmos is not just about mapping space. It is about grappling with the very conditions that make the mapmaker possible. This silent conversation with the cosmos faces a growing threat from our own illuminated world. The faint whispers of ancient starlight are being systematically drowned out by an artificial glow that now envelops our planet. For the majority of people living in urban areas, the true night sky has vanished, replaced by a washed-out orange haze that conceals all but the very brightest stars. This light pollution is more than an aesthetic loss. It is an act of cultural and scientific amnesia. We are severing our own connection to the cosmic stories written in the dark. The same glow that allows our cities to function at night acts like a constant, deafening noise, blotting out the delicate signals astronomers rely on. Observatories built a century ago in remote locations now find their views compromised by the expanding radiance of distant towns. The light from a galaxy 10 billion years old, a signal that has journeyed across the universe, is lost in the final millisecond of its voyage, defeated by the stray glare from a parking lot. This is not a metaphorical loss. It directly limits our ability to observe the most distant, and therefore the oldest, objects in the universe. Their faint light simply cannot compete with our own sky glow. The fight to protect our access to this ancient guide has taken two distinct paths. On the ground, a global movement has championed the creation of international dark sky preserves. These are protected areas where artificial lighting is strictly controlled, creating sanctuaries of darkness where the Milky Way can still be seen in its full, awe-inspiring splendor. These parks are not just for astronomers, they are for everyone, serving as a vital reminder of the universe we are a part of. Yet, ground-based efforts can only do so much. The ultimate solution has been to rise above the problem entirely. The development of space-based telescopes like Hubble and the James Webb Space Telescope represents the most decisive step in this quiet battle. By placing our observatories in the vacuum of space, we escape the shimmering, light-polluted blanket of our atmosphere entirely. Out there, the sky is perpetually, perfectly black, allowing these instruments to gather the faintest whispers of the cosmic past without any interference. This is not a luxury, it is a fundamental necessity for the future of discovery. Every new exoplanet atmosphere we hope to analyze, every distant infant galaxy we seek to find, every subtle ripple in space-time we try to measure, depends on our ability to collect pristine ancient light. Protecting the darkness is not about turning off our lights, but about managing them wisely, and when necessary, seeking the void to ensure the silent revolution can continue. Our future navigation of the cosmos depends on preserving our ability to listen to its past. This flood of cosmic data is more than any single research team could ever hope to process. The light from billions of galaxies collected by our most powerful telescopes represents a deluge of information that demands millions of human observations. To solve this, scientists turn to the world, creating projects like Galaxy Zoo. This initiative invites anyone with an internet connection to become a cosmic archivist, to look directly at the light that has traveled for millions of years and help classify the shapes of distant galaxies. Is that faint smudge a spiral or an elliptical? Is it colliding with a neighbor? Each click by a volunteer is a direct conversation with ancient light, a personal contribution to mapping the universe's structure. This is not a simulation, these are real images from telescopes, and the collective pattern recognition of the human brain often spots unusual objects that automated computer algorithms might miss. The public has helped discover entirely new classes of galaxies, like the green P galaxies, small, intensely star-forming systems that had been overlooked in the vast data sets. Beyond these organized projects, space agencies have embraced a policy of open access, releasing the raw data from missions like Hubble and James Webb to the public. This treasure trove of ancient photons is now available to anyone, from a university professor to a high school student with a laptop. Amateur astronomers and coding enthusiasts download this data, apply their own processing techniques, and sometimes spot something everyone else missed, a strange atmospheric signature on a distant exoplanet or a variable star blinking in a new pattern. This is the ultimate democratization of cosmic discovery. The silent guidance from ancient Starlight is no longer locked away in an ivory tower. It is a shared resource for a global community. It ensures that the next revolutionary insight might not come from a PhD in a lab, but from a curious person halfway around the world, simply looking at the sky with fresh eyes and asking a new question of the light from the past. This silent conversation with the cosmos is far from a purely academic exercise. It fuels a powerful engine of innovation with direct and tangible benefits for our daily lives. The relentless pursuit of capturing and understanding ancient starlight has repeatedly driven technological breakthroughs that later ripple through our entire economy. A perfect example lies at the heart of every modern smartphone camera. The charge-coupled device, or CCD, was perfected in the 1970s by astronomers desperate for a more efficient way to capture the faint light of distant galaxies. Unlike photographic film, these digital sensors could turn individual photons of ancient light into precise electrical signals, building a perfect digital image pixel by pixel. This technology, born in the vacuum of space observatories, did not stay there for long. It became the foundation for the entire digital imaging revolution. Today, the descendants of those first astronomical CCDs are everywhere. They are in the medical scanners that peer inside the human body to detect tumors with stunning clarity. They are in the security systems that monitor our safety, and of course, in the billions of pocket-sized cameras that document our lives. The same silicon created to see the birth of stars now helps bring new life into the world. This cycle of innovation does not stop with hardware. The overwhelming flood of data from our telescopes, the countless photons captured from billions of galaxies, created a problem that demanded a new kind of solution. How do you find patterns in a sea of cosmic information? The need to process this astronomical big data directly spurred the development of more sophisticated algorithms and machine learning techniques. The very tools that now power internet search engines, financial forecasting, and medical diagnostics were first tested and refined on the ultimate data set, the universe itself. The silent revolution in space exploration, guided by ancient light, is not a one-way street. It fuels a parallel revolution in technology and industry right here on Earth, transforming our world even as it helps us understand others. The ultimate extension of this silent conversation would be to find a reply. Our search for life is already reaching for the chemical whispers of biology in alien atmospheres, but a far more profound quest listens for the deliberate signal, the structured artifact, the evidence of a mind. This is the search for technosignatures, the hunt for intelligence itself written into the ancient light we collect. We are no longer just analyzing the natural state of a distant world. We are looking for the unnatural, for the subtle but unmistakable imprint of technology. Imagine the spectrum of a star, its predictable rainbow of colors, suddenly showing a bizarre and persistent dip. This could be the signature of an artificial compound, an industrial pollutant like chlorofluorocarbons that have no natural source and would scream of technological activity. Or consider a star whose total light output seems strangely dim, but its infrared glow is intense and warm. This is the theorized signature of a Dyson sphere, a colossal swarm of energy-capturing structures built around a sun by a civilization harnessing its entire power output. The light itself would be physically altered, its energy redistributed by the hand of a builder. The search extends even to the laser, a tool we ourselves use. A powerful, tightly focused laser beam, even from 1,000 light-years away, would create a momentary, brilliant spike in our detectors, a flash of pure coherence entirely unlike any natural stellar flare. These are not just science fiction dreams, they are concrete, physical anomalies that our telescopes could, in principle, detect within the river of ancient photons. This represents the final frontier of using light as our guide. For billions of years, starlight has carried only the story of cosmic physics and blind evolution. Now we have begun to sift through that same silent data stream for a different kind of pattern, one that implies purpose, engineering, and a consciousness looking back. The same light that tells us how a star dies could one day tell us that we are not alone in the universe. That cosmic horizon is the final frontier of our vision, a boundary set not by our technology, but by the nature of time and light itself. This is the limit of the observable universe, a perfect sphere centered on us with a radius of about 46 billion light-years. The reason for this limit is profoundly simple. The universe is approximately 13.8 billion years old, and light travels at a fixed, finite speed. This means the most distant light we could possibly see is the light that was emitted at the very beginning of the universe and has been traveling toward us ever since for the entire cosmic age. We cannot see anything beyond this horizon because the light from those more distant regions has not had enough time to reach our telescopes. It is not that those regions do not exist. The universe almost certainly extends far, far beyond what we can observe, but from our particular vantage point in space and time, they remain eternally hidden, their light still en route across the vastness. This observable sphere is our entire cosmic context, the only part of existence we will ever have direct evidence for. Every galaxy we have ever catalogued, every quasar we have ever analyzed, exists within this bubble. Our entire map of the cosmic web, from the first stars to the great walls of galaxies, is confined to this single, luminous volume. This limit is not a flaw in our methods. It is a fundamental property of a cosmos with a beginning. It guides and constrains our cosmological models, because we can only build theories based on the data we can actually collect from within our horizon. This realization brings a profound humility to our quest. For all our powerful telescopes and ambitious missions, we are ultimately studying our local cosmic neighborhood, a single island of the visible in an ocean of the unknown that may be infinite. The very starlight that guides us also draws the final line beyond which we cannot see, a silent reminder that the grandest truths of the cosmos may forever lie just beyond the reach of our oldest light. The silent whispers of ancient starlight are no longer our only cosmic informants. A deeper, more fundamental conversation has begun, one that listens not just to light, but to the very fabric of reality and the ghostly particles that slip through it. This is the dawn of multi-messenger astronomy, a revolutionary approach that combines the ancient guidebook of light with two other, even more elusive messengers, neutrinos and gravitational waves. Each one tells a different part of the story, revealing cosmic truths that would otherwise remain forever hidden. Neutrinos are among the most abundant particles in the universe, yet they are famously aloof. They are produced in unimaginable numbers by nuclear reactions, from the core of our own sun to the violent deaths of massive stars. A neutrino carries no electric charge and has almost no mass, allowing it to pass through entire planets as if they were not even there. Trillions of them are streaming through your body at this very second, completely unnoticed. This ghostly nature is their greatest strength as cosmic messengers. While a beam of light can be blocked or scattered by cosmic dust and gas, a neutrino flies straight through these obstacles without a single interaction. It arrives at our detectors carrying a pristine, unaltered signal directly from the heart of the cataclysm that created it, from places where light is trapped forever. Gravitational waves, on the other hand, are not particles at all. They are ripples in the fabric of spacetime itself, first predicted by Einstein. Think of the universe as a still, silent pond. A gravitational wave is the ripple that spreads outward when a massive object is suddenly disturbed, like two black holes colliding in a titanic merger. These waves do not travel through space. They are a wave in space, stretching and squeezing the distances between objects as they pass. Like neutrinos, they are largely unaffected by the matter they travel through, bringing us a direct, unscreened account of the most violent events in the cosmos. The true power of this new era emerged in a single, historic moment in August of 2017. For the first time, observatories detected the gravitational waves from the merger of two neutron stars. Just 2 seconds later, a space telescope observed a short, powerful burst of gamma-ray light from the exact same region of the sky. This was the trigger. Astronomers around the world swiveled their telescopes both on the ground and in space to that single point. What they witnessed was the birth of a kilonova, a brilliant flash of light created by the collision. The light revealed the forging of heavy elements like gold and platinum, scattering them across space. The gravitational waves had told us the how, the immense physics of the collision. The light told us the what, the chemical elements that were created. Together, they painted a complete picture of an event that had occurred 130 million years ago. This single observation, combining messengers from the gravitational and electromagnetic realms, marked a fundamental shift. We are no longer just watching the silent universe, we are feeling its vibrations and counting its most secretive particles. The ancient starlight that has guided us for centuries now has powerful partners, and together they are telling a story of cosmic violence and creation that is richer and more detailed than we ever thought possible. These images of ancient starlight do more than advance science, they fundamentally reshape the human psyche. Seeing the Hubble ultra-deep field, with its thousands of galaxies, each containing billions of stars, triggers a cognitive shift known as the overview effect. Astronauts who have seen Earth from orbit describe this feeling as a sudden, overwhelming recognition of our planet's unity and fragility. For the rest of us, these deep space images provide a similar proxy experience. That single frame of a seemingly empty sky, now revealed as a crowded cosmic metropolis, collapses the vastness of space into an intimate truth. We are living on a tiny, pale blue dot suspended in an immense ocean of suns. This cosmic perspective, delivered directly by photons that have traveled for billions of years, can dissolve the artificial borders we draw on maps. Our conflicts and divisions seem smaller when viewed against the backdrop of a universe teeming with galactic cities. This connection fosters a powerful sense of global citizenship, a visceral understanding that we share a single, precious lifeboat in the void. That realization naturally extends to a deeper commitment to environmental stewardship. The same silent light that shows us the grandeur of creation also highlights the unique and irreplaceable nature of our own world. There is no backup Earth in these images, no second chance visible in the swirling nebulae or distant exoplanets. The silent revolution, therefore, is not merely a story of technological progress. It is a profound philosophical and emotional journey. By allowing us to see our place in the cosmos, ancient starlight becomes a guide for how we might live better lives right here, nurturing the only home we have ever known. The faint whispers of the cosmos demand ever larger ears to hear them. Our next step in this guided journey is taking shape on remote mountaintops, where engineers are assembling the largest mirrors ever conceived. The Giant Magellan Telescope and the Extremely Large Telescope are not mere upgrades. They are colossal behemoths that will redefine our vision. Their primary mirrors, measuring 25 and 39 meters across respectively, act as gigantic light buckets. Their combined surface area will capture millions more ancient photons than today's best telescopes, transforming faint cosmic murmurs into a clear and detailed conversation. With this immense light-gathering power, these instruments will perform two revolutionary tasks. First, they will turn their gaze toward small, rocky worlds orbiting distant stars. They will not see continents or oceans, but they will do something just as profound. By analyzing the starlight that filters through an exoplanet's atmosphere during a transit, these telescopes will be sensitive enough to detect the chemical fingerprints of potential biosignatures. The subtle dip in a specific color caused by methane, or the telltale signature of oxygen, could shift from a theoretical possibility to a measurable fact. Second, they will function as the most powerful time machines ever built. They will gather the incredibly redshifted light from the universe's infancy, observing the very first galaxies as they flicker to life. We will watch them not as static, faint smudges, but as dynamic structures, seeing their violent mergers and their frantic bursts of star formation in unprecedented detail. These ground-based giants will push against the final frontiers of observation, asking the oldest light to reveal the secrets of our origins and our potential place in a living cosmos. These colossal new telescopes will push the boundaries of our vision, but they still face a fundamental physical limit. The ultimate sharpness of any single telescope, its resolution, is determined by the width of its mirror. To see finer and finer details on a distant exoplanet or at the heart of a galaxy, you would need a mirror of impossible scale, one spanning not just meters but entire continents. The solution is to stop building bigger mirrors and start building a smarter kind of eye. The next great leap will come from a technique called space-based interferometry. This ambitious concept involves launching not one, but several individual telescopes into the void, flying them in an exquisitely precise formation thousands of kilometers apart. By combining the light they collect with atomic clock precision, these separate instruments can act as if they are a single, gargantuan virtual telescope. The resolution of this synthetic instrument is not defined by the size of any one dish, but by the immense distance between them. A formation spread across the orbit of Mars, for instance, would create a virtual lens wider than the inner solar system. The potential of such a machine is staggering. It could transform a distant, blurry exoplanet from a single pixel of light into a recognizable world. We could directly image cloud patterns swirling in an alien atmosphere, distinguish continents from oceans on a temperate super-Earth, and perhaps even detect the surface glint of starlight on a foreign sea. Closer to home, but no less profound, such an array could peer into the chaotic hearts of distant galaxies, resolving the fiery disk of material just outside a supermassive black hole's event horizon in exquisite detail. We would watch in real time as matter is ripped apart and vanished from our universe. This is not merely a bigger telescope, it is an entirely new way of seeing. It relies entirely on our refined ability to capture, guide, and manipulate the ancient starlight we receive, weaving together its faint whispers from multiple vantage points to construct a picture of reality that no single instrument could ever provide. The silent revolution continues by learning to listen not just with one ear, but with many spread across the solar system, all tuned to the same ancient song. This flood of cosmic data has become an ocean, one that no human mind could hope to navigate alone. Every new observatory, from the James Webb to the upcoming giants, pours a staggering torrent of information into our archives, a deluge of ancient photons captured in digital form. The challenge is no longer about gathering the light, but about understanding it. We have moved from a famine of data to a feast so grand it threatens to overwhelm us. Hidden within this sea of numbers are the subtle patterns that could reveal the universe's deepest secrets, a single irregular galaxy among millions, or a faint, unexpected chemical signature in a distant star's spectrum. To find these cosmic needles in the haystack, astronomers are enlisting a new kind of partner, artificial intelligence. These are not conscious minds, but sophisticated algorithms trained to recognize patterns with a speed and scale that dwarfs human capability. A machine learning model can be shown millions of images of galaxies, learning the subtle differences between spirals, ellipticals, and irregulars. Once trained, it can then classify new galaxies automatically, processing in hours what would take a team of human volunteers years to accomplish. But their true power lies in finding what we are not even looking for. These silicon minds can detect anomalies, objects that do not fit any known category, or uncover subtle correlations in data that are invisible to our own senses. They might analyze the flickering light of a star and identify the minute dimming caused by a planet we would have missed, or sift through the spectra of a million stars to find the handful with a chemical composition that points to a truly ancient origin. This is not about replacing human curiosity, but about amplifying it. The silent guidance from ancient starlight is now being filtered, sorted, and interpreted by these powerful tools, accelerating the pace of discovery from a steady walk to a sprint. The universe is whispering its secrets, and for the first time, we have the tools to listen to every single word at once. That same ancient light guiding us to distant worlds now illuminates a profound ethical frontier. With every new exoplanet atmosphere we analyze, we edge closer to a moment that will redefine humanity's self-perception. The detection of a genuine biosignature, a gas like oxygen or methane in impossible chemical equilibrium, would signal we are not alone in the universe. This discovery, carried on photons that have traveled for centuries, would be the most transformative in human history. But what then? Do we immediately beam a reply toward that distant star, announcing our presence with a celebratory shout into the cosmic quiet? Or do we listen intently, gathering every possible piece of information before we even consider making our own noise? This is the core of a growing debate among scientists and philosophers. The potential risks of active messaging are staggering. We have no way of knowing the intentions or the nature of a civilization capable of receiving our signal. Our own history is a grim lesson in what can happen when a more technologically advanced culture encounters a less advanced one. The silence of the cosmos, what we call the Fermi paradox, might itself be a warning, a great filter that eliminates civilizations reckless enough to announce their location. On the other hand, the moral argument for reaching out is equally powerful. To receive a sign of life and then choose eternal silence could be seen as an act of cosmic cowardice, a failure of the very curiosity that drove us to look in the first place. It would be a betrayal of a fundamental human impulse to connect, to share knowledge, and to find our kin in the vast dark. This is not a distant hypothetical. Organizations already exist that broadcast intentional messages to nearby star systems, while other groups of prominent scientists argue vehemently for a mandated, global consensus of extreme caution. The starlight that reveals a potential new world does not come with an instruction manual for first contact. It only gives us the map, not the rules of the road. Our responsibility extends beyond mere detection to stewardship. If we find a world teeming with simple, microbial life, do we have a right to land, to explore its oceans, to walk on its surface? We could inadvertently contaminate a pristine biosphere with our own hardy Earth microbes, forever erasing the unique evolutionary path of that world. Or worse, we might introduce a pathogen that wipes out an entire alien ecosystem before we even understand it. The protocols for planetary protection are already strict for our own solar system, mandating that rovers sent to Mars are meticulously sterilized. But for a world light years away, the guidelines become exponentially more complex and philosophical. The silent light that guides our exploration is forcing us to grow up as a species. It compels us to look inward as much as outward, to question our own motivations and our readiness for a universe that may be far more crowded than we ever dreamed. This is the final and perhaps most important guidance the ancient stars offer, a mirror held up to our own wisdom, asking if we are truly prepared for the conversations that may one day begin.